right, lecture 1.3, a programming model for the ARM processor. This is part of a book I wrote with Garbedian Divine. I'm Dr. Picone. Check out the MIT Press website for the book and the book companion website, rtcbook.org. Okay, a programming model for the ARM processor. Program execution. A program instance is called a process comprising one or more threads or tasks. Okay, so a process is here, and then you're going to have thread or task. One thread or task. Two. Thread and task are synonyms. Okay. Real-time systems face challenges in scheduling tasks and managing shared resources like memory. Levels of abstraction. The application level is where programs written in high-level languages like C are living. And then there's the operating system level, which manages resources shared among tasks like processors, memory, and I/O devices. So if two different tasks want to use the same resource, like the same memory or the same peripheral device, the operating system has to arbitrate among those threads. Processor functionality. In our programming model, the endless repetition of three key steps. So step 1, fetch an instruction from memory. Step 2, translate the instruction. Step 3, execute the instruction. And then go back to step 1, fetch a new instruction from memory, translate the instruction, execute the instruction. This is how the processor functions in our programming model, the model that we're using as our understanding of what the processor is doing in order to write the programs effectively. Control unit and data path, the two aspects of the processor. The control unit fetches and translates instructions, directing the data path to execute them. The data path uses registers, which are small special purpose memory in the data path, as we've discussed, temporarily stores instructions, data, or execution results. And it has limited capacity, offloads to cache memory, main memory, or secondary memory. And as we go left to right here, we get slower to read and write from and larger capacity. Focus that we're going to have is to introduce an ARM processor programming model, which is an application level view for the ARM v7 instruction set architecture. Core ARM registers. Register overview. There are 13 general purpose registers. Yeah, they're labeled R0 through R12. There are 3 special purpose registers, SP, LR, and PC. We've got the stack pointer, the return link, and the program counter as our 3 special purpose registers, and we'll talk about how they work. The general purpose registers are used to store data such as integers, floating point numbers, and characters. The special purpose registers, stack pointer, SP, points to the top of the active stack used to temporarily store data. The return link, LR, stores the memory address of the calling program during subroutine calls, keeps our place where we are in our program. And the program counter contains the memory address of the current instruction plus 8 bytes, which is to say 2 instructions ahead, and it tells us where we're headed in our program. The other ARM registers, we have the application status register, APSR, which is a 32-bit register storing the status of the program's last executed instruction. Key flags, which have single bit encoding, so this 32-bit register, each bit has some significance. N is the negative condition, and it is turned to 1 for a negative 2's complement result. So we've looked at 2's complement binary, And if the 2's complement binary represents a negative number, this flag gets set, which means this bit gets set to 1. Z, the 0 condition, is 1 if the result is 0. So if the result of the operation was 0, this flag gets set to 1. C, the carry condition, it is 1 for unsigned overflow in addition. If we run out of digits in our representation of the number, then we'll get overflow. There's another overflow condition here, which is for signed overflow, V. And then Q, there's overflow saturation condition, which is used in digital signal processing, which we'll come back to later in the course. Includes a nibble, so 4 bits, for the GE flag, which is the greater than or equal to flag. Okay, execution state registers. Those were the application status registers. Here's the execution state register. Support special instruction sets like thumb instruction sets, which is a special instruction set, and then configures the endianness, so big endian or little endian, and we'll talk more about what that means in the next lecture. Vector floating point unit, VFPv3. There's the ARM v7a, optional extension for efficient floating point arithmetic, and includes dedicated floating point extension registers. So we'll often need to do a lot of floating point arithmetic, and these help speed that up. Okay, types of instructions. Examples of instruction types a processor might encounter: load or store, transfer data to and from registers. Very common type of instruction. We want to load into a register some piece of data and maybe store it in memory from the register, the result of some instruction. Transfer, move data among the registers. Move, relocate data elsewhere in memory. Set, reset bits, modify specific bits in registers. Shift or rotate, adjust bit positions. Arithmetic operations, addition, subtraction, multiplication, division, negation. These are arithmetic operations that we might want to perform, and so we have instructions for those. Logic operations, bitwise operations like and, or, etc. Conditional branches and jumps, execute based on conditions. So if this, then that, for instance. Unconditional branches and jumps, execute without conditions. So at this point, we go to another location in a program, for instance. Subroutines, call reusable blocks of instructions. Okay, finally, addressing modes. So how the processor is to calculate the memory address for a load or a store operation. For the ARM v7a instruction set architecture, an address has 2 parts, a base register value and an offset. Offset can be immediate, an unsigned number that can be summed with or subtracted from the value of the base register. The offset can be register, which is a value from a core ARM register other than the program counter, and scaled. Register a shifted value from a core ARM register other than the program counter summed with or subtracted from the value of the base register. So these are the 3 different offsets. These lead to the following 4 addressing modes. Register, which is the simplest. The memory address is the value of the base register. Okay, so let's look. I made a little figure down here. So if we have a base register that has the address 2 in it, if we're using the register addressing mode, that just corresponds to that address in memory. Okay. Now, there's also a pre-indexed. The offset is summed with or subtracted from the base register, forming the memory address. So say there's an offset of 2 here, and we're using pre-indexed addressing mode, then the address that's being referred to here is the base plus the offset. So it would be 2 plus 2, which would refer to 4 in memory, the address 4 in memory. Okay, so that's pre-indexed. Pre-indexed with write back. Same as pre-indexed, with a new address being assigned to the base register. So we would do the same as we did in pre-indexed. We would look up 4, okay? And then in the next step, we would replace, once we've looked up that address, we would replace the base with 4. So now instead of 2, we would have 4 there. And the next address we would look up would be 6. You can see how this could be useful if you're, for instance, looking through an array, right, that has some fixed offset in between each value in the array. Okay, post-indexed with write back. The memory address is the value of the base register. The base register is then offset. So the base register is used here. So let's go back to 2 and so post-indexed with write back. The memory address is the value of the base register. So 2 would be our address. Now we offset the base register. So now that we've looked up 2, for the next step, we're going to change 2 to 4, the offset of 2, and we'll look up 4 this time. And then again, we'll offset the base to 6, etc. So those are the different addressing modes, and they can be activated by using different instructions. So the form of the instruction that is given to the processor in our program determines which addressing mode is used. So that covers our basic programming model for the ARM v7a. We're going to take a deeper look at how this works with the paper computer in section 1.4. But before we do, we are at a point where we really need to review how binary number representation works and just numeral representation in general. So that's going to be next, section 1.3, and then we'll come back to the ARM programming model. All right, see you next time.